Hey everyone. So what we're going to be talking about today is actually we'll be starting a new chapter, chapter 3, which deals with exponentials and also their inverses, which are logarithms. So in section 3.1, our goal is really just to introduce exponential functions and also to graph them. So our main goals are for you to be able to graph a function given an equation, and we'll be looking at key features of the graph. And the secondary goal is for you to be able to determine an equation when you're given an exponential graph. So let's start off just by defining what an exponential function is. So an exponential function, which I'll call f of x, is any function in this form. In the form f of x equals a times b to the power of x. So just like we have our general format for linears, for quadratics, everything, we have our general format for exponential functions. Now in this formula, a is usually what's called the initial value if we're doing a problem with context. Or you might notice that 0, a is the y-intercept. So to show this real quick, if I plug in 0 for x, I end up with a times b to the power of 0. And this is a good chance to review our exponential rules. Anything to the power of 0 is just 1, so it would be a times 1, which just gives us a. And so that's why we know that this is the y-intercept. Also, in this formula, b has to be a number that's greater than 0, so that means b is positive, and b cannot equal 1. If b was 1, it would just be 1 to the power of x, which is not really exponential. It's just 1 when you do 1 to the power of x. Okay. All right, so exponential functions are kind of weird from what we've been doing because the x, in this case, is actually in the exponent. That's how you can identify these. That's why it's called exponential. So up till now, we've been doing algebraic expressions where x was not in the exponent. We did polynomials where x is to the power of 2 or 3 or 4. We did rational functions, which is really just polynomials being divided. So now we're switching gears a little bit, switching our brains to think about x in the exponent. So let's start off, now that we've defined it, let's talk about a graph and define a couple key features of the graph. So when I graph an exponent, I always like to start off with the function 2 to the power of x. This is a pretty common one because this represents doubling. Everything is being multiplied by 2 over and over again. So we're going to go ahead and graph this function. Notice that a in this case is just 1, that's why I didn't include it, and b is 2. Okay, now to graph this to start off with, I'm going to use a t-chart, a table, and I'll start with some negative x values like -2, -1, we'll hit 0. Let's go up to 3. Okay, so we're going to do f of -2, which is 2 to the power of -2. Another good chance to review some exponential properties. The negative in the exponent means that you actually have the 2 squared in the denominator, which is 1/4. In order to graph this, I will actually write down the decimal approximation here, 0.25. I'll do a couple more. So I get 0.5. And then we already talked about 2 to the power of 0. Everything to the power of 0 is just 1. 2 to the power of 1 is just 2. 2 squared is 4, and 2 cubed is 8. So I'm doing 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Whoops. Got ahead of myself there. Okay. So there are the points on my graph. Now we could actually graph those. So I'm going to need -1, -2, and I'm going to need 1, 2, and 3. And then on the y-axis, I'm going to need all the way up to 8. Okay, so let's plot our points. Over on the left side, it's going to be about 0.25, and then we hit 0.5, 2, 4, and then 3, 8. So the graph looks to me on the right like it's going to continue up forever. That's what we call exponential growth. And then on the left-hand side, it sort of curves around, and it actually never touches the x-axis on the left side. Okay. So a couple things to define here. We have our y-intercept. Is at 0, 1. We have the asymptote in this case, just like we had with rational functions, is the x-axis. So that would be the line y equals 0. You could just say x-axis. Notice that the asymptote in this case is only kind of on the left side, so it would be as x goes to -infinity, y goes to 0. So that means that these lines here are getting closer and closer together. We could talk about the domain. So in this case, for the domain, we could have all real numbers. There are no issues with exponentials. Notice in our table over here, we plugged in negative numbers and positive numbers. I could plug in fractions. I could plug in all sorts of stuff, whatever I wanted, and I would be fine. The range, however, is going to be limited. The graph always remains above the x-axis. Even over here, it stays above the x-axis. So the range is going to be everything that is bigger than 0, and it can never actually equal 0 either. So these are the key features that you need to have written down in your notes somewhere. This is my go-to example for an exponential function, so that's a really good one to have in your notes. And I think I'm going to be ending the video at this time.